So this is something that we talked about before when we were talking about the zeroth law. But there it was discussed in the context of a particular system, the ideal gas. But you can actually define the thermodynamic temperature scale, which is, we choose that to be the Kelvin scale, in a context which is independent of a particular system. That is, in the context of some idealized Carnot engine. Okay, so what is the setup? The setup is that suppose that we have two Carnot engines. So we have two Carnot engines, and one is run between the temperature T1, which is greater than 1. This is Carnot engine number 1. And the second one is run between temperature 2 and temperature 3. Now, the work, so for a Carnot engine, we know that the work done is given by the temperature at the hotter temperature, the heat that is absorbed at the higher temperature minus the heat that is dumped in the lower temperature. And so it's, and we remember that we defined the efficiency, eta. Now we are going to write the efficiency eta. So, a Carnot engine is essentially defined by the two temperature reservoir that it acts between, right? So we have a reservoir here and a reservoir here, and we have an engine, and then there's the work, right? So that's basically, so what work is going to come out is determined by, because the Carnot engine has the highest efficiency, and we saw that the Carnot engine. So the efficiency of a Carnot engine is going to be determined by these two temperatures. And the efficiency was defined to be, how much of the heat that is absorbed from the higher temperature reservoir is converted to work. And that is given by QH minus QC divided by QH. So this is the efficiency of a Carnot engine. So now for our first Carnot engine, we can rewrite this formula. So we can write this formula as the lower temperature, say the heat dumped to the reservoir, the lower temperature reservoir, is equal to Q1, 1 minus eta T1, comma T2, right? Can you see that this is basically this formula? Because if I divide out by this, the first term becomes 1. The second term is minus QC by QH, and this 1 we keep on this side, and we bring this guy over here, and QC over QH we bring over here, and then QC is equals to QH times 1 minus eta. So this is what we get, right? And for the second Carnot engine, we similarly find that Q3 is equal to Q2, 1 minus eta T2, T3, right? Now, what we can do is that, so essentially what we're doing here is that we are running the second Carnot engine off of the heat that is going into, that is being dumped by the first Carnot engine, right? So the heat that is being absorbed by the second Carnot engine is the heat that is being dumped by the first Carnot engine. So that is how we have set up the whole thing. Now, if I combine these two formulae, I can say Q3 is, I can eliminate Q2 from these two guys, and I can express Q3 as Q1 times 1 minus eta T1 comma T2 1 minus eta T2 comma T3. Okay, any questions so far? So the key here is to realize that the second Carnot engine is the heat that is being absorbed by the second Carnot engine is the heat that is being dumped by the first Carnot engine. Okay. What exactly is Q1, Q2, Q3 referred to exactly? Okay. So okay, right. So these are, so that's one of the questions that came out. So we have, say T1 is a reservoir at some temperature T1, and T2 is another reservoir, and this is my, this is absorbing the heat Q1, and this is giving up the heat Q2, okay? And this is the work that is going out. And then, so this is Carnot engine number 1. And then we have another Carnot engine number 2. What is happening here is that we have, say, T2, and it's taking in exactly the same amount of heat and giving out some other lower amount of heat and turning such that I don't think the work it has to be the same. So yeah, I don't think so. So this work is W1, and this work is W2. Okay, and this is T3. So what is important here is that this Q2 is equal to this Q2. Okay. Question is, sir, two Carnot engines have the same value? No, they don't have the same efficiency, no. We are not assuming that these two efficiencies are the same necessarily, okay? We will find the functional dependence of eta on the temperature. That is our aim here. Okay. All right, so, and then what we can do is that we can say, okay, we can consider these two Carnot engines to be the same Carnot engine. And then the picture becomes something where you're going from T1 to, say, T3, and in between you have a third Carnot engine, but now the heat going in here is Q1, and the heat going out here is Q3. And so Q3 now is Q1 times 1 minus eta T1 comma T3. Okay. Now if I compare this with this relationship, see that on the left-hand side we have Q3, which is the same, and the right-hand side we have a functional dependence. So we have Q1, but here we have a functional dependence on T1, T2, and T3. But over here we have a functional dependence only on T1 and T3. That means that the function, the dependence on T2 from this formula must drop out. In other words, if I equating these two equations, 1 minus eta T1 comma T3 is equal to 1 minus eta T1 comma T2 times 1 minus sorry sorry what I'm saying is that for the T2 dependence, to drop out, we have to assume that eta, say T1 comma T2, must be of the form of, say, some function of T2 divided by some function of T1, right? And we can choose this function, and this function is chosen to be just a linear function T. And then we have that, the T2 dependence will drop out, and these two equations should agree. Let's verify that they do agree, because when I was writing the lecture notes, I actually didn't I didn't appreciate this point. So let me just see, make sure that, so if I look at make sure that it does happen, right? So if I look at the right-hand side of this, that should be equal to this, right? Do you guys agree?
Yes, sir. This should be good.
So this should be 1 minus eta T1 comma T3. And according to our solution, this is 1 minus, what is it, T3 minus T1, right? And then, so this should be, and then on the other hand, the other guy is, over here is this thing, then that is going to be 1 minus eta, this should be, say, T2 by T1, right? And here this should be 1 minus T2 by T3. And then the first term is 1, and then we have minus T2 by T1, and then this is plus, right? Because this is this times this, and then we have this times this, which is plus T2 by T3. And then over here we have minus minus. So what am I doing? This should be minus sign, sorry. Did I make a mistake? I think so, yeah. Sorry, this should be the other way. This should be T3 by T2, right? And this should be T3 T3 by T2, and this should be plus T3 by T1, right? So, and what is this? This is T1, T2, and so we get T2 squared minus T1, T3. So this should be 0, right? I don't. There should be 0. I don't know why. Sorry. Let me just see why. Because I think. Am I missing something here? What do you guys think? Because it's just not enough. I mean, this term. So this is. Do you think I'm making a mistake here, or what am I? Let me see if I have made a mistake. Yes, of course. I'm an idiot. Sorry. It's this thing. We have to assume that, right?
Yes, now it makes sense.
Yeah. Good. Yeah. Sorry about that. Yeah. Anyway, but I too am human. Good. No, I mean, I think it's good. It's good to have confusions like this live in class, so you know that your teachers are human too. And not only that, it's a mistake that you won't make. I won't make again in my life. So okay, good. Right. So we have found that the thermodynamic scale is, we can choose the thermodynamic scale to be such that temperature scale, such that the efficiency of a Carnot engine is given by 1 minus T2 over T1, right? Yeah. All right. So I would have been much happier if one of you could have figured out what the mistake I was making. But anyway, I'm happy that it was found out. All right. So any questions?
So I think I'm missing something, but I feel like I don't know what's going on here. Exactly what we're trying to do with this part.
Oh, yeah, sure. So the thing is that, previously, we said that there was a temperature scale and it was a monotonic scale, right? So, and that monotonic scale. So the thing is that, like, two objects, where, two objects were at thermal equilibrium with each other if there was a function which, as a function of the state, say I'm denoting that state by theta by 1, if they were equal, or but it could have been that that condition was also satisfied if suppose there was a square root. So I don't know if you remember when we first talked about temperature scale. Let me go back to that quickly. And the way we we're talking about, so we are talking about the zeroth law, right? And we're saying that, remember the zeroth law said that if you have three objects, say A, and then B and C, and A is in thermal equilibrium with C, and B is in thermal equilibrium with C, then the zeroth law tells us that A is also in thermal equilibrium with B, right? And there we, remember that we said that, well, if these are fluids, then of course their states are specified by, say, P and V. So there is P1 V1, and there is, say, P2 V2, and then P3 and V3 for, say, for ABC. And the idea was that if A was in thermal equilibrium with C, there must have been some relationship between these values and these values, that there must be some function like f of AC, we called it, which was a function of P1 V1 and P3 V3, right? And
Yeah.
there must also be the same function, but with A and C replaced by B and C, and P2 V2 replacing P1 V1, because these two guys are in thermal equilibrium, right? But this relationship allowed us to invert this and express V3 as a function of everything else, right? And then we found, by similar logic, there was a relationship between, say, A and B. But we also found a relationship, the same relationship, but it included it included V3. And the only way that the V3 dependence could drop out was that if this function f of AB, sorry, there was like I think not a V3, there was a P3 dependence, that there was another function which was a function of A, and P1 and V1 was equal to that function, which was a function of B and P2 and V2. Remember this kind of argument that we'd made? Because then, the P3 dependence dropped out because they canceled out. Because this guy canceled out with this guy. But for the cancellation process, we actually could have said, okay, this could have been just this as well. Any monotonic function of theta was good enough. Why was it that we took for that cancellation, not the monotonic function, but just the linear function, right? And there we said that, okay, well, because if I look at the ideal gas, for the ideal gas, this turns out to be just T. And that's how we defined the temperature previously. But we were using the fact that this was the positive square, the positive number here, real number in the over here, was 1 based on a particular system. But what we showed here is that we can define a thermodynamic temperature scale simply on the idea of a Carnot engine. We don't have to specify what the particular system is, okay?